A lot of times the heat that you put into a substance will raise the temperature of that substance. But sometimes if the substance is at its boiling point or its melting point, the heat that you put in changes the state instead. So for example, if you are at the boiling point of a substance, then the heat that you put in will vaporize that substance. It will cause it to boil. And the heat that's needed to do that is proportional to the amount of substance. We are going to use mass or grams as the amount of substance. So if you have twice the amount, it's going to take twice the heat to boil that much substance. And then, of course, it depends on what substance you are trying to boil. So each substance will have a heat of vaporization. That's how much heat is required to boil or to vaporize each gram of substance. So some references will give this quantity in joules per mole, but we haven't covered moles, so we are going to be using joules per gram or calories per gram for our heat of vaporization. This looks similar to the specific heat, but there's no degrees Celsius in the unit because there is not a temperature change that is happening in this process. So the temperature is missing from the equation here. Instead of having mass times specific heat times delta T, we just have mass times the heat of vaporization. So we already have some ethanol at its boiling point for this first problem. And we want to know how much heat is needed to boil that much ethanol. So it's already hot enough to boil, we just need to boil it. And that takes 846 joules for every gram of ethanol that you are boiling, and we have 62.7 grams of ethanol. So the grams will cancel, and we will end up with joules. And my calculator is telling me 53,044.2 joules. We only have 3 significant digits in our heat of vaporization, and also our mass only has 3 significant digits. So we are going to want to round this to 3 significant digits. The problem with this particular example is that if we write the answer like this, because the 4 is small, so we keep the 0 as a 0, if we write the answer like this, it looks like it only has 2 significant digits. If we put a decimal, it looks like it has 5 significant digits. So we don't want to show 2 significant digits, and we don't want to show 5 significant digits. To show 3 significant digits, you could write it like this with a little underline under the last significant digit, or you could even write the subscript method. This 0 is significant, so we write it as a normal size, and the other 2 that are not significant can be written as a subscript. With a large number like this, it's a little bit strange. It might look like just 530. You can write it with an underline, or you can write it in scientific notation. With scientific notation, you only keep the 0 that is significant, and you can get rid of the zeros that are not significant. So all of these 3 ways are ways to show 53,000 with 3 significant digits. So this problem has a little bit of a significant digit issue in how we show that. Let's try another problem with boiling water. Water is very difficult to boil, much more so than ethanol. Every gram of water needs 2,256 joules versus ethanol, which only needs 846. We multiply this by the mass, and the grams cancel. We are left with joules. We have 4 significant digits here and 3 here. So we are going to want 3 in our final answer. This time it's going to be a lot easier because the last significant digit is not going to be a 0. We can just write it this way without the decimal, and that would show 3 significant digits. You can write it in scientific notation if you want to, but this time it's not so tricky. Heat of fusion is very similar. This is the heat required to melt something rather than boil something. But melting something also does not need a temperature change. So the entire time that something is boiling or something is melting, it will be at the same temperature. So the heat that's going in is not changing the temperature, it's changing the state. So for these previous problems, while the ethanol was boiling, it stayed at 78.4 degrees the whole time. While the water was boiling, it stayed at 100 degrees for the whole time. Now we're going to melt some solid ethanol, and it's going to stay at negative 114 degrees Celsius the entire time. So we don't have a temperature change. We don't need the temperature in the equation. We just need the heat of fusion and the amount, which we are using mass for that. So we have 106 joules per gram, and we have 81.8 grams. The grams cancel. My calculator tells me 8,670.8 joules. However, we only have 3 significant digits in our measurements, so we'll go ahead and round this to 3 significant digits, making it 8,670 joules. So this time we're going to melt some water. Again, it's a bit more difficult to melt water than it is to melt ethanol. Not quite as big a difference as for boiling, but the heat of fusion in joules per gram times the amount in grams will cancel the grams and give us joules. So my calculator gives me 145,958 joules. We only know that to 3 significant digits. So our final answer should be 146,000 joules. I wanted to show you what is happening to a substance as you add heat. So it does not make a smooth curve or a smooth line. At first your substance might be a solid. So here in area A is where the substance is a solid. And as you add heat, the temperature of that solid, the temperature is on the y-axis, the temperature is going up. Once you reach a certain temperature, then the temperature stops going up and the solid starts to melt. So G is the melting point temperature. Or you can also call G the freezing point. The melting point of ice is the same temperature as the freezing point of water. It's the same temperature. It just depends whether you are adding heat to melt something or removing heat to freeze something. Once all that heat has been added to melt the substance that is solid, then the substance is liquid. And if you add more heat, the temperature of that liquid will increase. So B is where the solid is melting. So we're going from solid to liquid, and there's no temperature change. So we'll call this delta T for a temperature change. There's no change in temperature. And C, we have a liquid, and the heat is making the temperature increase. Then once this liquid gets hot enough, the liquid will be boiling and there will be no change in temperature. So the liquid will be changing to gas without a change in temperature. It will stay at temperature F the entire time, which would be the boiling point temperature. At the end of curve D, once all of the liquid has become gas, now we have a gas, and if we keep adding heat, the temperature of that gas will increase. So we can have a gas that's quite hot. Let's take a look at what we want to calculate in problem 3.6.5. So we are going to warm some liquid ethanol from one temperature to another temperature. And then once it is at that temperature, which is the boiling point, we are going to also boil it. We're going to convert that liquid ethanol to a gas. So we're starting with ethanol as a liquid and increasing the temperature, area C of the curve. So here we are starting at this temperature, which is 25.5 degrees Celsius, and we have to bring it up to this temperature. The boiling point of ethanol is 78.4 degrees Celsius. So we want to add this much heat to bring it up to the boiling point. So this is heat to raise the temperature. This is how much heat is needed to do that step. Once we've raised the temperature, we want to convert all of the liquid ethanol into gaseous ethanol. So we're at this temperature, the boiling point temperature, and we are going to convert all the liquid into gas. And that is going to take more heat than if we just brought it up to that temperature. We're going to need to put some more heat in to boil it. So we have heat to raise the temperature and heat to boil the ethanol. So the total heat we're going to need to add to do both of these steps is going to be the sum of the heat to do this first step plus the heat to do this second step. So kind of like if you wanted to go from one location to another location and then from that location to a third location, then the total distance you have to travel is the distance to get to the first place plus the distance to get to the last place. So we are going to add both of these steps to get the total heat. So we are doing two things to ethanol. We are warming it from 25.5 degrees to 78.4 degrees. So the heat to raise the temperature of something is the mass times the specific heat times the change in temperature. So the change in temperature, all right, I lined it up to see that it's going to go one past the decimal, but there's not really room to write it underneath. So I'll write it over here, 52.9 degrees Celsius. And we can keep it one past the decimal, so we can keep all three significant digits. So we'll multiply the mass times the specific heat times the change in temperature. The degrees Celsius and the grams both cancel, and we are left with joules. My calculator tells me 5,947.1238. However, all of these have three significant digits, so we'll go ahead and round that down. Step A needs 5,950 joules to do step A. To boil something, it is the heat of vaporization times the mass. So we have 846 joules per gram of ethanol when we are boiling it. Right now we're working with 45.7 grams of ethanol. The grams will cancel. My calculator gives me 38,662.2 joules. Again, we have three significant digits because of the measurements, so that would get rounded there. And so step 2, boiling it, takes 38,700 joules. The total heat of both of the steps together is the sum of what we need for each step. Let's go back to our original numbers to add them up. We'll just keep track of where our significant digits are. For step A, it was in the tens place. For step B, it was in the hundreds place. When we add these, we get 44,609.3238 joules. We have uncertainty in both the tens place and the hundreds place, so we are going to round this to the hundreds place. And the total heat for both of those steps together is 44,600 joules, with uncertainty in the hundreds place, plus or minus 100. The answer key that I have typed up ends up coming to 44,700 because I rounded it at each step and I added both of these rounded numbers, but that's okay because this is the uncertain digit. So if some people got 44,700, that's okay as well. Okay, for this problem, we are starting with some ice, solid water, at negative 18.2 degrees. We want to add some heat to increase that temperature to the melting point, which is 0. So this heat is to increase the temperature of ice. Then we want to melt the ice and get liquid water. So we are going to need to add some heat to melt that solid ice into liquid water. And then we want to get this liquid water to be 36.8 degrees Celsius. So here are our temperatures in degrees Celsius. Starting at negative 18.2, we want to increase that to 36.8. But it's not just a simple line. It's actually happening in 3 steps. First, we're heating it up and increasing the temperature in a linear fashion. Then we have a little break where the heat is not increasing the temperature. It is melting the ice. And then we have another chunk of heat that is heating the liquid water from 0 to 36.8 degrees Celsius. So we're increasing the temperature of the liquid water. I had to get the graph out of the way, so let's go ahead and write this in a list form. So part A, the first thing we need to do is to increase the temperature of the ice. The change in temperature of the ice is going from negative 18.2 degrees Celsius to the melting point of 0 degrees Celsius. After that, we can't change the temperature of the ice anymore because the ice will melt and we'll have water. So the final temperature of the ice minus the initial temperature of the ice gives us an 18.2 degrees Celsius increase. It's a positive change in the ice temperature. So it's going up by 18.2 degrees Celsius to get to 0. And that heat is the mass times the specific heat times a change in temperature. So we have 33.7 grams. The specific heat of ice is 2.027 joules per gram degrees Celsius. And we are going up 18.2 degrees Celsius. And my calculator tells me 1,243.2 joules, but we should only have 3 significant digits, so I will just underline that one for now. Once the ice is at 0 degrees Celsius, we are going to melt it. It takes 334 joules per gram, and there are 33.7 grams. I haven't been canceling my units, so we'll go ahead and cancel grams. Here we cancel grams and we cancel degrees Celsius. So we have joules. Here we also have joules. 11,255.8 joules with 3 significant digits. Now we have liquid water and we want to increase the temperature. Going from 0 degrees Celsius as our initial temperature to 36.8 degrees Celsius as the final temperature gives us a positive 36.8 degree Celsius temperature change. Multiplying that temperature change by the mass and the specific heat, we'll cancel grams and degrees Celsius, and we'll end up with joules for this one also. So this is 5,188.8 joules, again with 3 significant digits. And the total heat is going to be all of these amounts. So this one for warming up the ice, this one for melting the ice, and this one for warming up the water. And we're going to add all these together. All right, here I tried to keep them color-coded. I'm adding up all 3 of these steps. The first step, 1,243.2 plus or minus 10. The second step, 11,255.8 plus or minus 100. And the third step, 5,188.8 plus or minus 10. That adds up to 17,687.8. The uncertainty is both in the hundreds place and in the tens place. So we're going to have to round it to the hundreds place. And that gives us a total heat of 17,700 joules as our final answer.